this up just in case we need it. Okay, so how is everyone doing for the hot field assignment? So I guess, yeah, let's start by catching up with if you guys have any questions or issues from last time. Yeah, for the hot field network, even though we're done with that, but you guys are doing the assignments now. Any questions that come up you want to ask now? Now would be a good time to deal with it. Any? Or everything is smooth so far? Really? That's good. Any questions? No? Can be anything. It doesn't have to be like very deep. It can even be like some coding issue or whatever. All good? Okay, and how about conceptually? In terms of as you're coding, are there any concepts that you guys don't get, or like you don't understand why this code is done this way, or what hot field, how we're trying to implement a hot field, or how does a given code actually do the hot field kind of conceptualization? Okay, so if not, then we're going to assume that we can close the hot field for sure. I mean, close in the sense that that part of it, we're done with the classroom introduction of it. But actually, in fact, hot field will sort of come back again in the last model that we do, sort of, because we will use the notion of auto-encoding. In fact, even in Backprop, the assignment, there will be some sort of reference to auto-encoding as well, the concept of it at least. And then also in your own future implementation, maybe in the future you still want to you want to deal with neural networks, you will find that hot field network, or at least auto-encoding, the concept of it, will come up again, in one form or another. So we close it, but it is still an active kind of question, okay? All right, then in that case, today we will talk about backprop. And backprop, so I'd like to kind of give a kind of a informal kind of introduction to this notion, okay? To give people a linkage with how our thought process is going. So first, just to highlight to you that even ChatGPT and like all the LLMs right now, all of them are using backprop, essentially, okay? Maybe, in some little tweaks and whatever, but the core of it, the core approach has always been a backpropagation kind of approach, and you'll see what that really means. But the key is, I hope you've read the chapter from Rumelhart and McClellan, because they start out by introducing the notion of error, or error-based learning. So yeah, I should kind of, backprop or backpropagation. Okay, as a kind of a learning algorithm. Okay. In implemented in many LLMs, CLMs, you name it, that you can kind of refer to or have heard of today, they are all implementing some form or at least had a kind of initiation from the notion of backpropagation. Backpropagation of what? Specifically, backprop of error. Okay? And you will hear also that this notion of error therefore calls on the notion of reinforcement learning. Okay? Now, so, and this is where we want to kind of refer to Rumor Hart's chapter there. The very first part, they talk about the delta rule. Okay? Which is the core or the heart of error-based learning, okay? Error-based learning or reinforcement learning, they are used in the same sense. I do have to qualify. This is what they say and what many people say. I personally don't think that error-based learning and reinforcement learning should mean the same thing. They do mean the same, they are used to mean the same thing now. I'm just saying that if you think about it, the notion of error and the notion of reinforcement actually psychologically is a different thing, okay? So, but because everyone has been using it, the label and the terminology have kind of stuck. But I urge you to go and think about it yourself. Should error-based, the notion of learning from error, be exactly equal to the notion of reinforcement learning? And I would argue no, okay? We can talk more about that later if people are interested or want to debate things, okay? But at least I'm going to present it in this class as it is taught or as it is used commonly, in which is that error and reinforcement learning are equivalent, and they refer to or they rely on the notion of the delta rule. The delta rule being that error is about a target output that deviates from, or a target state or target output really, that's what they care about. It deviates from a target, sorry, I shouldn't use E, sorry, I should use delta, okay, from the actual output. Okay, they start with this notion that learning relies on, is based on the delta rule. It's called delta rule because it is all the learning signal or the learning information is captured in the term delta. That's delta there. And delta is exactly equals to a target output minus an actual output. You will know the terminology I use here is the same as for the Hopfield in the sense that the AJ is the subsequent state, which suggests that there is an input, an AI, right? But right now we're talking about an AJ, and beyond that we introduce this new term, which is AT. AT is some sort of a target or desired or reference, okay? In other words, in many ways you can describe it, but it is some sort of a state that you want, but what you actually get from the network's actual output might be different, and to the extent that it's different, that's what delta is, okay? And you use this difference, and you learn from it, okay? So that the goal, or the problem set, we're always talking about problem set, is such that we want delta to approach 0, right? because that means that our actual output is equal to our target output, right? i.e., we minimize, right? I.e., the goal is to minimize delta. All right? It's very simple, that basic notion, okay? And you might also hear, and this is a good point to introduce, that this is called the delta rule, but you might also hear, and I'll use the next page to do this, just to note, because I think this is healthy, so that you see this form in other literature and other kind of disciplines as well, okay? We call this error-based learning. All the terms that you might hear, they are all very, very much correlated in the literature, okay? Error-based learning, as we said, is very commonly used to be equivalent to reinforcement learning. Okay, these are some terms to look at. And then delta rule, when they say that the system uses the delta rule to learn, they mean that it uses error-based learning or it uses reinforcement learning also. So these so far are equivalent. You will also hear Rescorla, Wagner, rule or learning, okay? And actually we will be using that because the idea here is that the delta is used in the Rescorla-Wagner algorithm, which incorporates a learning rate and all that. So we will be seeing that in the updating function later on. But again, it is used to equivalently refer, like when I say the RW rule, I'm talking about error-based learning, I'm talking about reinforcement learning, I'm talking about using the delta rule. Okay, so you will, and recently you will hear also temporal difference learning. Okay, temporal difference, the difference in this case where the delta is, it's about the difference between the future states and the current state. The future state being some desired state or something. And you want, and it is to do with time. So it's like a little bit more extension of these generic ones, but at the heart of it, it comes from, it is evolved from the delta rule or the Rescorla-Wagner rule itself, okay? So it's like, at first it's just error, but then if you take the notion of, well, but error can, one of the errors can be about how I am now versus how I want to be in the future. And then we talk about how far in the future, right? And the idea is I want to reduce that difference as fast as possible, okay? And if I do that, it kind of explains how my behavior changes over time. That at first I take a long time to do something, but after a while my actions become much more automatic, much more primed, okay? So the temporal difference learning is kind of like, well, that's a horrible star. Yeah, the temporal difference learning is a special instantiation of, or evolution of the original error-based learning. And I think it works quite well because I think as a model, it does seem to account for a lot of behavior, and there might be, it also makes it easier, sort of gives us a path to link behavior to actual biological neural network operation. And so this is very exciting. However, we won't talk about it. We won't deal with this extension in class, in this class. We will just stop at, okay, so sad. We'll just stop at this Rescorla-Wagner part, or at least the concepts of it, okay? Because this is, totally, once you go into there, you can go into another whole lecture or another course on its own, okay? But just to let you know, this is where things are at with respect to error-based learning, okay? The concepts, the terms. And also, please note that with regards to where we're at in this course, remember, so framing is very important. We started, okay, in this course, we started at the single layer perceptron. Okay, where we ask about to solve, we asked it to solve logic gates, logic problems. Okay, no problems there. Then from there, we went to autoencoders. Okay, it's specifically the hot field network, instantiation of it. And we asked it to solve content addressable memory. Okay? And so up to this point, the single layer perceptron is about mapping input to output but in in a very restricted way. You will find that the single layer perceptron can only do linear mappings. This is the mapping. Okay? So a single layer perceptron is really a mapping function, and it's a linear one at that. Okay? If we wanted to do the XOR problem, you realize it can no longer be a single layer perceptron. And this is kind of like jumping to what we'll do today. So that's where we were stuck at with single layer perceptron. We wanted to map inputs to outputs, but it had to be linear. The mappings had to be linear, okay? When we went to autoencoding, we also did some sort of a mapping. Solving content addressable memory is also sort of a mapping, okay? But it is about an input state, more about input state mapping to an encoded state. There's not, strictly speaking, any output in the auto-encoding help field instantiation, right? You just kind of squeeze information into the network and then hope it stays there. You can try to retrieve it out, and that could be the output. But in its operation itself, it does not really have a goal that it wants to have an input to output mapping. It just wants to have an input encoding state, some sort of an embedding, okay? And so now, and this is why it's good to talk about this now, when we talk about backprop as a learning algorithm, using the delta rule, using reinforcement learning and all that as a learning algorithm. So auto-encoding, we are talking about hot field, and specifically hot field, the learning is Hebbian learning, okay? Remember, it's 2at minus 1 square, okay? It's just short form, right? It's 2a minus 1, 2a minus 1, and 1 is transposed, but this is just the shorthand of it. That's Hebbian, okay? But here, we're using a learning algorithm that is backpropagation, which is error-based learning, okay? And whereas at the very beginning, we use a single layer perceptron, here we will start talking about a multi-layer perceptron. And therefore, and this is the magical part, okay? If it is a multi-layer perceptron, And with respect to the original problem where we map linear inputs to linear outputs, so a constrained class of input-output mapping, right? Only linear ones. Versus we encode, can be nonlinear relationships, but we are not doing any input-output mapping. We're just doing input embeddings, okay? Input embeddings. Here now, and this is the very, very profound thing, we are mapping input to any output, as if like there's no constraints at all. Okay? It's like I just want to find any association I can find between input and output. It doesn't matter. Doesn't have to be linear. It can be nonlinear. You know, it can do embedding. It can do anything. That's the challenge. That's the claim here, i.e., the proposition is that this algorithm can do anything. Seriously, okay? Essentially. And if you look at LLM and ChatGPT these days, sort of true, isn't it? It literally can do anything. Think about it, okay? Seriously, think about it. Is there anything that the LLM cannot do right now in terms of information mapping? You can give it pictures and it can give you pictures. You can give it sound, it can give you sound. You can give it smell. Technically, it can also sort of give you smell if you hook it up right to some right machines, the right smell. Okay? Right? I think the only challenge now is emotion. However, I do not think that that is a challenge of its algorithm. I think that's a challenge of us, that we do not understand what is emotion yet. Or at least we haven't translated emotion to a embedding, some sort of encoding representation yet. We haven't done it in our, human knowledge yet. But if we one day do that, then we can translate that sort of to a digitized state. Then LLM can do it. Okay? I'll put this out there because I say this provocatively. It can do anything, okay? But you can think about it. If you have arguments where you think that, no, there's some things you can't do or whatever. If so, okay, yeah, I would actually very much welcome discussion about it, or if you in your answers and all that, we can talk about it. Okay? Okay, so therefore, in backprop, okay, the goal the overarching goal is to use the minimization of delta to map anything to anything. You guys must have heard of what is it? All these networks, functions, algorithms, machine embeddings, and all that, they are trying to find an embedding so that they can map any format to a vector. And the vector, if you go back to our arithmetic, is a projection of the embedding in some sort of hyperspace. Okay? And in a minute, I can find this embedding in this hyperspace. I can therefore use it to produce or interact with other kind of vectors and whatever to change the basis or to move around or to define the basis and do all sorts of crazy mathematics with it, okay? But that's essentially what the neural network is doing. It's a matrix in that array that encodes an embedding that maps whatever format to whatever format, and in so doing projects it into a hyperspace position, and then you can do geometry on it, okay? And in geometry, therefore, you can move around and move from one state to another, and that's essentially what these neural networks are doing. The LLMs are, you give it some input, it spits out to you some movement along some embedding space, okay? All right, so this is the grand goal, all right? And this is, keep in mind that this is what we are doing, and how we arrived at here with respect to the single layer perceptron, the autoencoder, and now this one. So presumably this one should be very, very powerful, okay? And I guess we have a lot of daily live examples of how powerful it is, okay? Okay, so that's the overarching goal. And from here on, I'm going to kind of work through some proofs, okay? It might get a little bit mathematical, but, and you should not panic. You are not required to know how to prove it, but I'm doing this because if you have done the reading, I'm just basically digesting the reading for you. The reading in Rumor Heart is getting you to think why they arrive at this reinforcement learning, this backpropagation algorithm in order to solve this problem, this problem set, okay? Yeah, this one, okay? That, I mean, this is a grand challenge and I can solve it in many, many ways. They are suggesting, okay, Rumor Heart, actually it's Hinton, right? Jeffrey Hinton, the Nobel Prize winner, okay? Is suggesting that this way, the backpropagation of error is a very robust way at least, and seems to be mathematically sound, as we will see, okay? In that if you use delta to do this backpropagation of learning from errors, you achieve gradient descent in the weights. And we will see what gradient descent is and why it's so cool, okay? Incidentally, if you have seen Jeffrey Hinton's, so I think it's good to note, proposed by Hinton, okay? This is what proposed by Hinton. Use delta, okay, to achieve goal. And that's why he won a Nobel Prize, okay? In physics. All right? Hinton proposed that if you do this, you can achieve that goal. And of course, that's really the goal we want, right? We want to do anything. We want to be able to do anything. So Hinton is saying, use delta, then you can do anything. I mean, maybe, okay? So incidentally, I raised Hinton is because if you had a chance to read, he's done some interviews online, and in some of the interviews he talks about his kind of career and thought processes. He started out, I mean, he's a computer scientist, but he started out with a neuroscience psychological question, right? The reason why he wanted to do all these things is because he wanted to know how the mind and brain works, actually. Okay? So, I mean, I don't know. So, it used to be in Nobel Prize world, right? It used to be Nobel Peace Prize, Nobel Literature Prize, and Nobel Prize for mathematics, physics, and chemistry, all this kind of thing, and biology. And when Edward Moser and O'Keefe won the Nobel Prize for finding grid cells, place cells, right? You're neuroscientists and psychologists. So you're suddenly a psychologist, you feel like, wow, psychologists can also win Nobel Prize, right? Finally, right? And then, because it was unheard of. So there are certain barriers in Nobel Prize. First, one of the biggest barriers previously was that the battle between physics and mathematics. Then after that, it was battle between men and women, okay? And then it was about the now like other soft science fields also is considered. And now it's like psychology is in there, so we are like, yes, you know. And it's becoming more common because although you say that this is the Nobel Prize for physics, and he's a computer scientist, but he's asking a psychological and neuroscience question, okay? So I dare say that because of AI and because of technology, we are now, maybe the world has now matured and can finally ask the more important psychological questions. So if you want to see it that way, right? Okay, but I just want to highlight this because it's like he started from this point and then moved towards this. And it's likely, I think that's the trend of future science, that more and more people will be asking about so-called more abstract psychological questions and not just restricted to the physical notions of it. Okay? All right, so this class, for the rest of this class, I'll be going through the proofs. The proofs are meant to digest and summarize what the readings on Backprop are trying to present to you, okay, are trying to argue to you. And their argument, the goal of the argument is to convince you why backpropagation can solve that problem of mapping anything to anything, okay? All right, so let's start. So backprop proof. And we start, as always, to define the problem set, okay? What is the problem that we want to solve? The problem in this case being, as we have stated before, map any set of inputs arbitrarily to any set of outputs. Okay. By definition, therefore, this goal requires the operation to be referring to the notion of symbols. Okay? So, really, because it's arbitrary, right? It's like A, B, C, D, they are symbols that represent a sound. Why did I have to have this A-looking shape to mean A, the sound? There's no reason. I could have used some other star shape to represent the sound of A. Okay? It's very arbitrary. But it worked so that when I write the letter A, your brain evokes all the sound A. Okay? So your brain did it already. Okay. Let the input AI, and I have two dots here. Okay, so the subscript indices are going to be very important, very, very critically important. Okay, so pay attention to them. What this means is I have the ith layer. So I'll use a different color. Okay. And then kth node. This will be, I will unpack this even more later on. And the S state. Okay, so my subscripts, if I have subscripts that go like, 1, 2, 3, they refer to layer first, then node, then state. Okay? That's why I have a dot, dot. And if I put a dot there, okay, dot implies all of that index range. Okay? Meaning not a specific instance of it, I'm referring to that the summation over all of it. So if I do AI dot, I mean AI all the nodes. Okay? If I mean a specific node, I will do AI k, or AI k equals 1, or AI 1. Okay? All right, so please note the notation convention here. So let AI dot dot be the following input pattern vectors over so k units. Okay, so the units are nodes. Okay, that's interchangeable. And S states. Okay, so that A, I, S by K. All right. I have, let's say I have input units. I have 1, 2, 3, 4, 5, 6, 7, 8. Let's say I have 8 units, just like your hot field, you have 16 units, right? So let's say I have an 8 unit one, and I can have 16, 64, whatever. Okay, so the kth unit refers to this I mentioned here. And I have many states of these. So this is like an 8-bit vector right now, right? But this 8-bit vector can change states. And we will operate in binary worlds still, okay? Because more or less binary world, for inputs at least, okay? It's easier to operate in binary world for the most part, okay? But actually you will see quickly we do not, we move very quickly from it. These states can change, so you can be, this vector can be the simple one that we had before, like that. 1, 0, 1, 0, 0, 1, some whatever random thing you want. Okay, etc. This is the problem set. Then you want to map it so that let AT, remember that's the target output that we want, dot dot be the target output, okay, pattern vectors over R units corresponding to each input state S. So that we also have a table, a data table, S over K, and 1, 2, 3. So at first, we have the input table, nothing surprising there. Nodes, input node K nodes by S states. But that should correspond to target output states, which has R nodes and also S states, okay? So that the critical thing to note is that N of K is not necessarily equal to n of r, where this is input units, output units. Okay? Okay, so let me put it together. In other words, we have A state over K okay, and this is like 0 or 1, all right? And we want to map it, find the relationship to which can be binary as well, should be binary as well, okay? Right? And that's the question. What is this magical W, okay, that will map AI over S over K to AT over K over S and AT over R over S. Okay, always start with defining this data tables that you want to solve so that it makes it very clear. So in other words, that's the question. Therefore, to express it formally, it is like this, right? Put an S here, okay, over S. That's right, yeah. Okay, so this mathematically formally expresses the challenge. That basically what we want is to solve W, given that we have a function that takes W and input states over states to produce some target output or some output, okay? But we don't know what this function is and we do not know what it will produce yet, but we want it to produce AT, okay? And for any AI and AT. Okay, so what is this magical W that will be able to do this? Okay, that is a very big mathematical problem already. All right, so Hinton proposes this. Or the chapter or Rumelhart also proposes this. They're all colleagues, they work together. Okay, proposes to consider this. Sorry. So we have an architecture from the chapter. Just like Hopfield proposed the architecture where the nodes are connected to every other node except themselves. That is the Hopfield network. Hinton proposes that we can consider an architecture such that AI, I'm using vector notation, okay? So although I'm drawing blocks, this really is a vector, right? Okay, and is linked to I'm going to make the qualification that this is not H subscript 1. this is H1 itself is equivalent to I, all right? So that I can actually have H1, K1. Okay, so otherwise I'll run out of letters very soon. So I will keep it such that this is H1 and it has K1 nodes, okay? So the number of nodes in I is it has K nodes, right? And N of K nodes. The number of nodes in HI, layer HI, is it has N HI nodes, H1 nodes, okay? All right, so the number of nodes in layer AH1 has N H1 nodes, whereas AI has NK nodes. Sorry, no. The number of nodes in AH1 is NK1, okay? And yeah, and then so the number of nodes here is NK1. The number of nodes here is NK. Okay, so that the 1 there is not a subscript. It's part of the label of K, all right? So I get that very clearly. So I would be careful to write it at the same height. Okay, if it's at the same height, it means it's the same level. Only if it's a bit lower, then it's a subscript. Okay, so what that means is that you have Y is H1, okay, and H1 stands for hidden nodes, hidden units. So this is input. We have a hidden. Yeah, sure. I can do another one. This is why I need H1, because I could have H2 or H3, H4, etc. Okay? Okay, it's also hidden. Let's do it this way. As in, I can have as many H's as I want before I finally reach the output. So Hinton proposes this architecture. Yep. And if you have these units in these hidden layers, they are connected to each other as follows, right? And although there is a possibility that I have more hidden units here, I'm going to assume that there isn't right now to make the the array, the connecting weights make more sense. Okay, Hinton proposes this architecture that we have input nodes connecting to hidden nodes and eventually leading to output nodes. The connections between the nodes have the array W corresponding to the prior node to the subsequent, the next layer nodes, okay? And finally, when you get the output, which is AJ, you evaluate AJ against AT. And in so doing, you are achieving this function of W, okay, with the input to give you AT. All right? But you do it by evaluating AJ, applying some evaluation function of AJ and AT, okay? And so to unpack this a little bit more, I'm going to erase this part, yeah, and I'm going to use because I think it's easier to view it this way. Let's go into a bit more specifics. Let's assume that AI has 3 units, okay? And AH1 has 3 units, and AH2 has 3 units. It doesn't have to be, okay? And AJ only has 1 unit, let's just say, all right? In that case, the label is such that this is AIK, this is AIK equals to 1, AIK equals to 2, and AIK equals to 3. Okay, no problem there, right? They connect to via WIK equals to 1, H1 K1 equals to 1, WIK equals to 2, H1 K equals to 1. Okay, and see, I'm really spending time here because otherwise it will get worse and worse. Okay, K1, sorry, K1 equals to 1. So that this is obviously A, H1, K1 equals to 1. Okay? And let's keep going. Okay, I won't belabor the rest, but this will be okay. We have to do this because when you code it, you will get a headache. And if you do not get the fundamentals and are aware of where the indices are, that's why I say the indices are going to be very important here. We haven't started the nightmare yet, okay? This is just laying it so that reduce the pain of the subsequent nightmare to come, okay? Because when you code it, you will get confused if you do not know which node, at which layer, at which time you are talking about, and in which direction. For now, we are doing this. Hinton proposes this architecture, and specifically this architecture is, as I have described it like this, is a fully connected, right? It is fully connected. Every node is connected to every node in the next layer. And in the next layer, meaning that it is feed forward in terms of activity. Whoops. Activity is feed forward in that I stimulate the inputs, and that forward stimulates the hidden, and forward stimulates the next hidden until I get the output, okay? And it is, and I can describe this as K to K1 to K2 to R, in that this is the official description. You can write that 3 units, 3 units, 3 units, 1. So this is a 3, 3, 3, 1 fully connected feed forward multi layer perceptron. Okay, so this is 3331 MLP. This is the terminology. So I can say something like 842 MLP. You'll be able to draw it out. I can say something like 2250. You can draw it out. I can do like 4432820 You can draw it out. Okay? MLP. Okay? So by that token, you actually can draw out an LLM. An LLM is like how many billions by how many billions, how many billions, how many billions to how many billions. Okay? It's why you need massive machines. Okay? Any question about this? All right, so the worry here in this class is like, when you talk about things like this, it seems like, wow, LLMs and all these complex things are actually not very complex, in the sense that it is very, very concrete and, you know, you can grasp it. And the fact is that it is, okay? It's just that when you scale things, and as we said before, the key for neural network simulations is that it cannot be computed analytically. You have to actually run it. That's where the complexity comes out, okay? But in terms of its conceptualization, and you know, if people really spend time to describe things to you, you'll find that it's actually not so hard, okay? All right, so if you're okay with this, I'm going to finish up one part first and then we'll take a break, okay? If we have that architecture in the previous slide in mind, and that's Hinton's proposal, that we have that architecture, and we implement that architecture such that, if you have it in your notes, you can refer to AH1 K1 is going to be equals to some function 1 of not K anymore, but AI dot all the nodes, right? All the inputs, correct? If you go back to the graph before, AH1 K1 is equals to some function, because you see the weights, right, of all those weights modulating all those inputs. So it's some function of the input node activity with the incoming weights modulating those input node activities. And this function will give rise to whatever AH1K1 is going to be. Okay? Similarly, likewise, if we keep going, you can see where this is what is going to happen. Oh, sorry, I left out that this is going to be H1, K1. Yeah? Make it cleaner here. So that this is going to be H1 H1 dot H2 K2 AH1 dot. Okay, you see the pattern? And because I only have 3 layers, yes? It's a chain. It propagates. So propagation. Okay, input leads to the next activity, which that leads to the next activity, which that leads to the next activity. So this is the propagation. wave, the wave function. Okay, and when you understand what we mean by wave functions, we can go a lot into physics and all kind of stuff, but we won't. Okay, we'll just stop it at that and have you realize that when it is a network like that, fully connected feed-forward, it's actually a wave function. Wave functions are very interesting, okay, in physics. It should be interesting for everything, pretty much, because here's the cool part. Nope. Let's put it at the same level. It's at the same level. Okay. What is AH2? What is AH1? AI. Cool, yeah? That is AJR, the output, is equals to some big combined function that takes in H star J of the input. Okay. So this is what ChatGPT is. This big F. It really is. And it's a wave function. Very complicated one, but it is no doubt. Okay? And I like to think of things this way. I will present this to you and we'll take a 10-minute break. What it is you have a pool of water. It's a wave function, right? You have a pool of water. Okay? At the edge of those pools, of the pool, are the output positions. The possible, like the pool boundary is defined by all possible output positions you could arrive at, okay? And the input is where at first the pool is flat, not disturbed. What the input is you go and dip your finger in one part of the pool, and then there's a wave that propagates, right? Now, depending on the shape of the pool, the wave is going to hit one boundary first, or some boundaries, some locations. And the state of where the wave propagates and hits that's your output state. It may be the one you want, may not be the one you want. If you don't want it, change your shape of the pool so that the output state is the one you want for any given position that you start. Okay? And it is a wave because it starts from some input. It can only propagate to the immediate water molecules, right? Physically, any input cannot jump to escape some water molecules and then just like teleport its activity to some further molecule. It can only perturb its neighbors. That's what a wave has to do. Okay? And it will do it, but and how it does it depends on the shape of the pool. It also depends on the content of the water. Maybe the water is not even, it's not all uniform. Maybe here the water is hotter, here is cooler, right? And if the medium has inconsistency, that's going to affect the shape of the wave, right? So all of that is this big F. And your dipping your finger is the AI. And the big F, which is actually the W, right, that constitutes the big F integrating with the AI, will give you the shape of the pool. that you have. That's the way I think about it. All right? Any questions? No? Okay. All right. So I'm going to put it there and let you digest it. We're just starting, okay? It gets worse. All right? And so we'll take a break, 10 minutes, and then we'll come back and then we'll really go into the nightmare. Okay? All right. So let's do a 10-minute break and we'll come back. Hey.
我觉得应该只要知意可以跟我解释那一条。
No one here. Oh. Okay, let's start. So where are we at? Okay. So the previous class we talked about the fact that the backprop is a wave function, and then it goes from the input, and then you have weighted activity that modulates the next hidden state, that modulates the next hidden state, and so forth until you reach the output. Okay, this is the architecture. And at this point, we haven't specified what's the function. We just know that, well, whatever function it is, whatever activation function it is, it will propagate like that because of the architecture. Okay? And we haven't also specified the learning rule, right? So the weights are like fixed at this point. It's like as if we already have the weights, okay? And we already have the fact that that's how they are connected to each other. And so therefore, it will have this property of Aj is equals to some big function, which consists of the weights of all the hidden layers and the input perturbation, initiating input perturbation. So then how do we go from here? So at this point, good to remind ourselves, recall that our goal, okay, is to solve W such that delta equals AT minus AJ approaches 0. It's minimum, minimizing it. Okay? Also, let's reframe that AJ is equals to that big F of this big W, okay, IHJ A input. And this implies, this is Hinton's math happening, that if I were to take the derivative of AJ, differentiate, 微积分, okay, told you it's going to get crazy, okay, and this is actually going to have this form of it. Let's do G prime as the derivative of big F, okay? I'm just basically using formal notation here. Nothing genius about this math, but it's genius in terms of mathematical conceptualization, okay? Is that if I have Aj is some function of W and Ai, then the differential, the derivative of Aj, how Aj changes as a function of the change in the weights is going to be some different integrated form, derivative of the big F. Let's call that G prime, okay? And it takes the input, correct? No problem there, right? So if this is okay, therefore, find the function, not the derivative of it, but the original function, okay, such that some candidate function we call E, okay? And that it's derivative by weights, okay? So we know that the output is changing by weights is given by this mysterious derivative function, okay? Let's put a placeholder and let's say we don't know what this function is. Let's call it E first, so that it has to be such that this original function, not the derivative function, but the original function, okay, G, not G prime, okay, such that the change of this mysterious quantity as the weights change implements gradient descent. Okay, let me unpack that a little bit more. We want to minimize AT minus AJ. Okay, and we know the architecture has this propagating property. Okay, so that gives us this big F. But we do not know how to compute W such that it will give us this ability to do AT minus AJ approach 0. We want to know how to compute this W so that AT minus AJ will approach 0 given the architecture. Okay? So, I don't know. So let's see what we can guess and then see a candidate quantity we can use to feed into the W such that if I had this quantity and I use it in the W to change, to calculate W, then I can get it such that the AT minus AJ will be minimum. Okay? That's what this all means. That's what the gradient descent, and with respect to this quantity, mystery quantity. Okay? That's why we have to have these components set up. That's what is the candidate. The hypothesized quantity, we do not know yet. Okay? So that if we have it, if we know it, then we can implement gradient descent. Gradient descent will guarantee that it will be a minimum. We will achieve this minimum that we want. Okay? Unpack that graphically. What that means is that yeah, so some mysterious quantity changing by weights, that's going to be a woof. How do I do back? Okay. Yep. Okay. It's a negative gradient. Okay. No matter whether delta is, so this is the delta quantity here. No matter the size of delta, okay, this gradient, which is d mysterious quantity by dw, is always going to be negative. Okay? And so that if my weights are changing as a function of this mysterious quantity, okay, over here on the left, to go towards the minimum, I have to be increasing my dw. My dw has to go in the positive direction, right? Okay? So the change in dw is positive, okay? But it is in the negative range. So in other words, I will have a negative quantity, okay? If I'm talking about the gradient, okay? So that if it is dE by dW here is negative, right? It's negative direction to go towards the minimum point. But over here, my dW, if I want to go to the minimum, I have to go in the negative direction, right? So that oh, sorry. Yeah, correct. No. Where's my name? Okay. Yeah. Let's change this. I'll do it this way, like this. Yeah, okay, that makes better sense. Okay, so if I'm on the left side, my dE by dW is already negative, so that the whole result is a negative gradient. Okay, but if I'm on the right side, I want to make the equation go towards the minimum. All right, because the gradient there is positive. Okay, I have to make it negative. All right, so that the dW will be negative going in the minimum direction. So in other words, I always want my dE by dW as a whole to be negative in order to achieve this minimum gradient descent. That's what gradient descent does, okay? So that if you have, after we work out some crazy math later, if you have a situation where the dE by dW is negative with respect to the delta, that's why you have this thing on the left here, you will get gradient descent. That is the logic, all right? Okay, so we have to find some mysterious quantity E that will, if we work it out according to the architecture, according to our learning rule, according to our activation function, that it will give us this property that the change of this quantity by the change of the weights is always negative, okay? Then we will know that we have a gradient descent situation, all right? Because it will have this, this graph relationship. Okay, so like I said, math is going to be a bit crazy, all right, but that's what it is. So what is this mysterious quantity? Hinton, consider a quantity E, okay, such that dE by dW is equals to G. We want it to be the actual function, not the derivative of it, okay, is equals to, oh sorry, we use chain rule, okay. This is where the crazy math comes in. Anyone has a problem with that, chain rule? Okay, right? dE by dW is equals to dE by dAj multiplied by dAj by dW, right? The AJ cancels out, all right? And we want to know this, what this is. Try E is equals to half sum over, you know, K nodes or whatever, right? E.g., right? Or R nodes, rather. AT minus AJ squared. Try this. Okay, why try it? Okay, why this weird number? Well, okay, because if you try it this way, okay, because remember, our delta is AT minus AJ, right? This is the part I don't like about engineers, okay? Just guess some nice numbers, and then, oh, see, it works. But why? Why did you do that? It doesn't really explain it very well. Because it is mathematically intuitive, that's all, okay? But there is no other deeper reason, as far as I can tell from reading, okay? But why? Because he wants these two things. The delta is AT minus AJ. He wants to know an E such that if you get the derivative of it, you get something like nice like that. So if you realize, because dE by, I believe it should be d delta, yeah, it's equals to 1. This is delta. Yep, correct? That's it. That's why you use half AT minus AJ squared. It's because if you derive it with respect to AT AJ, you get 1. Neat. You don't have to worry about the derivative being different from, so to speak. You don't have to worry about the derivative and the original function's relationship because they scale to 1. Okay? They're related by scalar of 1. So that i.e. E is equals to half of delta squared. That's it. Okay? I guess it has a nice geometric property too, because if you understand what delta squared is, it's the area, and it is half of the area, so it's kind of like a statistical geometric notion of that the function is a symmetric, non-redundant representation of the total variance. I think it was by chance. I don't think there was anything conscious about why they chose this thing, okay? But it fits nicely. So let's play around with this candidate E, which is the half AT minus AJ, and such that the delta is indeed AT plus AT minus AJ, okay? So if we carry on with this, so that remember it was dE, remember that it was dE by dW is equals to dE dAJ dAJ by dW, okay? So I'm just copying it there. Let's take this part, okay? dE dAJ is equals to d dAJ. What is E? Right? That's why we have this candidate function, so we can plug it in. And let's see what happens. Yep. Okay. Open it up. D dAJ AT squared minus D dAJ 2, yep, 2 AT AJ plus D dAJ A. Okay, those of you fast, you can see what's going to happen. Yep. What's this? Right? Sorry. Where is it? No. So remember this and remember this. So delta is equals to minus. It's always minus this. It's negative. The relationship between dAJ dE by dAJ, okay, against delta is always going to be negative. So if I were to plot it out, oh, sorry, yeah, I need another step. It's not complete yet. So just this part, the dE dAJ part, okay? We still have to worry about this, right? Okay, because the dE by dW is this part, which is the negative delta part, okay? But we still have to worry about the dAJ by dW. So what is that? Okay, so then the dAJ okay, note, okay, so let's put that for note that AJ is equals to AI, right? That dot product, okay? Such that, excuse me, excuse me, dAJ is going to be a I. in a linear sense, okay? So the derivative of dAj by dW is itself AI, because Aj is equals to the dot product of the weights and the input. Okay? Linear. This is the linear case. All right? Because I haven't linear because I haven't put any activation function yet. Okay? All I've done is just assume first the linear instance where the W multiplied dot product by the A gives me the output. So therefore, the change in the output as a function of the weights is equals to the input. Okay? Therefore, if I go back to that equation again, D equals to dE dAj, I'm writing this so many times, too many times, is equals to minus delta AI. Okay? Or that delta AI is equals to minus dE by dW. Okay? So if I plot it out, what do we get? What we wanted, right? Which implies right? That the gradient is always negative. It will always lead us to a gradient descent. This is the mathematical proof why using the Rescola-Wagner rule, the delta quantity, as a derivative form of the half AT minus AJ squared, okay, is going to work to minimize the delta to 0 because of the architecture that we have, okay? But this is the linear case, right? As I said, because I'm only just using Aj is equals to W product, dot product with AI, okay? So this is the linear case. What about, and in neural networks, so in a linear case, this is analytically determined. I do not need to run any simulation. It is linear, so it is completely, I can just compute this quantity. I do not need to run any simulations at all. So remember, in neural networks, the value of the neural networks is such that okay, actually, Aj is not equals to AI like this, rather, right? But, oops, rather, Aj is equals to, remember, that weird big function AI. AI, okay? A function of it. I never specified what function. There's just F1, F2, F3, you know, and there's big F. If F1 and F2 and F3 and F are equals to 1, then it's the linear case, okay? But we never said what F1, F2, F3 are. So let's suppose a scenario where it is not 1, at least first. We don't know what it is, but let's say it's not 1, okay? So we have to, because up to this point, this proof works if we use the assumption that f equals to 1. Okay? So we know that if the relationship, the activation function is that f is 1, so that aj is equals to the dot product of w and ai, then we get gradient descent. What if f is not equals to 1? Do we still get gradient descent? Okay? So let's do this case. Let change in w is equals to actually, we don't need that yet, sorry. Doing it too fast. Okay. Now, delta aj, delta ai is equals to, as we proved just now in the linear case, okay, it's negative gradient descent. This implies that delta is equals to dE dW AI. Okay, can just move it down, negative. Okay, and WAI is the function. It's a linear instance of the function, right? But it is the place of that function. So let's put a more general case of the WAI function, and let's call it f, where f could be 1, in which case it would be the original linear case. Okay? But let's see what happens if we do not assume that it is 1. So you will see that if you use again the nice chain rule trick, you can do this again. Okay? It's important to note that I'm inserting a j, okay? But the df is using ai. This is important because one is input, one is output. Okay? So with respect to whether it's respect to input or output, it makes a difference. Okay? Now, simply, this is actually quite simple. So that term, okay, this one, dAj by d big F W AI is equals to the derivative, right? Because it's dAj by di of yeah. Okay, I'm just re-expressing that. And this term is equals to AT minus AJ. It's actually delta. Okay? It's proportional to it. It's equals to it. That implies that delta is equals to, in the case where it is nonlinear, in the case where the function is not necessarily 1, then it's simply that the delta becomes the same AT minus AJ, right? But modulated by the derivative of the weighted inputs. Okay, so just to, in the previous case, delta was AT minus AJ, was just AT minus AJ. Okay, right? But if it is not, if the not linear, if the activation function is not linear, then delta becomes the AT minus AJ quantity, but just modulated by whatever the derivative of the nonlinear function is. That's all. Okay? So that, and do note that because this is important, this is for output layer. Okay, and we do have to make this distinction because it's important it will be different encoding. So in other words, and I think it was somewhere it's negative. Yeah, okay. So in other words, if I were a linear case and I got the gradient descent, okay, and my f function, my activation function is 1, then my delta is very simply AT minus AJ. But if I want to get gradient descent, and my function is not necessarily equals to 1, well, it's very simple. I just make my delta is equals to AT minus AJ, but modulated by that nonlinear function. That's what Hinton is trying to tell us, okay? But the thing is, it is AT minus AJ. Now, AJ only pertains to the output layer, right, in the model, the right final layer, okay? But what about the other hidden H's, right? What do I do about it? How do I use the delta, okay? And so he also goes further to tell us that for hidden units or hidden layers, it's different. So that's why this is really a nightmare. I don't really like it for this reason. Okay? If it is not output layer, for hidden layers, then that function there, okay, I'm adding the summation over R because now, so remember R is the output number of nodes for the output, right? It is AJR, right? So summing over R, okay, the derivative of that mysterious quantity, or half AT minus AJ, over that function of f I input using chain rule. D E D F, yeah, this one's preserved, but this one changes so that it becomes DAJ W over K, and so K is the hidden layers, okay. One is DE. Yeah, it turns out that the rate of change of the weighted inputs by the change of the outputs is the slope between the outputs to the unit, right? The ratio between the input and output is the weights, okay? So you can actually get this third function, and if you realize what this is actually, oh yeah, there's a negative sign. I should always put the negative sign. So the negative sign is here. The negative is sum of R, sum of K of the weights from the output, okay? Because change of sorry, why am I? This is wrong. That's why. That's delta. Sum of this over delta r. Okay? dE over d function of E was what we had before already, and that's delta r. And so that for the hidden delta, as opposed to the previous delta was just AT minus AJ multiplied by the derivative of AT minus AJ. So just to remind you that this one is equals to AT minus AJ right? This is output delta. This is hidden delta. It's important to distinguish because the output delta has the target delta, the target activity you want to compare with. But for the hidden layer, we don't have any target hidden level of activity, right? So how do we compute a hidden layer delta? So that's why you see that if you work through all this math, the delta H, it has the component where it integrates or it includes the output. So I'm going to say this is the output, okay? Multiplied by the weights, multiplied by the integral derivative functions. The derivative of the weighted inputs, sorry. So just to highlight that this is output, input, input, output. This is about output, input, input. Here it's about hidden. Output, 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 output. Okay? So that the hidden weight, the hidden delta is computed based on the output delta, but modulated by the weights of the output layer that the hidden node is connected to, okay, and modulated by the overall activation functions derivative. Okay, this is very abstract. I'm going to make it more concrete in the next slide. I will draw out the network and show you where all these terms are. That's why this is a nightmare, okay? Because Hinton doesn't actually spell this out for you, where all the terms go and where they come from. It takes a while to digest, okay? And that's what we're going to do the next. But we have to understand that's what he's trying to do. It's because of the math. He realizes that when you try to get gradient descent by using the delta term, okay? The delta term, the first problem is, okay, we can prove it using linear activation function. And he moves on to go like, it also works even if the activation function is nonlinear, just that you have to qualify the delta, okay? All right, so we know we have to qualify the delta and we get the gradient descent, but the qualified delta also still depends on the AT. AT only applies at the output layer. What about the inside, the hidden layers? Because hidden layer units, we don't have a target activity. Output layer units, we have a target activity. But hidden layers, we can't just use the desired target activity and apply it on the hidden units, right? Doesn't make sense. So how do we do it? Well, he works through this math to show that, well, what you do is you take whatever the output delta is, and this is where the backprop is happening. Okay, this actually proves the backprop or instantiates the backprop because the hidden delta is backpropagated from the output delta, modulated by the connection between the output node with the hidden node. That's what these two terms mean. Okay, that's what all this math is trying to kind of, if you speak it in English, that's what it means. All right? Okay? I'll draw it out so it becomes super clear. But we have to go through the math to show you, to demonstrate the necessity of it, because it is a necessity from the mathematical derivation. Okay? So although, simply put, we want to implement that architecture that he proposed using the delta rule as the learning function and some nonlinear activation function, right? So we have the architecture, the learning rule, and the activation function. Although we want to implement it that way, he is trying to demonstrate to us the necessity, mathematically, the necessity that first, using the delta rule will give you gradient descent if we assume linear activation function, okay, given the architecture. Second, using the delta rule qualified by a little bit of the derivative of activation function is a general case of gradient descent. So in other words, it doesn't have to be linear. It can be nonlinear as well. Okay, so he's showing that. Then he's showing that not only that, the delta rule computes the delta for the output, for which we have a clear target. Okay, and if we apply backpropagation of the output computed delta, right, propagated through the weights that connect the output to the hidden, okay, the gradient descent will work. I mean, that all that comes together. So in other words, we have a delta rule with backpropagation, and that's why this is backpropagation of error. Okay? Or the complete term is error backpropagation, right? So in other words, Hinton's famous model is error backpropagation. And he goes through all this math to arrive at that. Okay? Now, I'm not going to scare you. You don't have to know all the math to do the neural network. Okay? The math is just to tell you the story of how we got here. And you can decide for yourself whether you are satisfied with his approach. I've just outlined you his thinking process. That's how he started. You can see that it is very different from Hopfield's process, isn't it? Okay, Hopfield's process is, let's go by Hebbian learning, because I saw that neural networks that fire together, wire together. And then I came up with the 2a minus 1 equation, which is the Hebbian learning. That's why. Okay? And then I work it that way, and then I can do memory. Hinton's reasoning is, I realize we learn by reinforcement. We learn from our errors. Every time we get an error, we make less of the error, right? So how do we do that? Well, there's the Rescola-Wagner rule, the delta rule, and then we know that our networks feed forward, and then we have some error, and then because the math or whatever, we find that it feeds back, and we can apply it in the nonlinear general sense. For me, I feel like that's where it's lost me, okay? Because it's kind of like the only psychological bit here is the error. The fact that we do learn from how much, when we do something, how far we are from what we want to do, okay? And then we change our thinking so that the next time we do it, we are more in tune with our desire. But I would argue that after that, or whether it's generalizable and whether it's backprops and all this kind of thing, there's not any neural plausibility consideration there, and nor is there any psychological kind of concept happening here, isn't it? It's all just mathematical necessity. Okay? It's not that it's wrong, it may be right, but at this point, I cannot see any paper or any study that have shown that our brain really does error backpropagation, and our brain really does sort of this nonlinear gradient descent thing, that is what our brain is trying to do. Okay? Unlike the Hopf fields, I can see that yes, our brain has some sort of a Hebbian learning, and our brain has this notion of attractor states. Seems that way. However, I find it harder to see how our brain has error backpropagation. Okay? The initial starting point makes sense to me. This is not a critique of this, because clearly this algorithm works, is earning a lot of money, more than the Hopf network. Okay? It's a brilliant engineering solution because it maps anything to anything. It does. Okay? But the goal is different. Okay? So I'm outlining this math to you now so that you can see the guts of it, and then you can therefore make a fair comparison of this with how you understand the Hopf network, which we went through the guts of it as well. Okay? Ordinarily, if you just use the code and script, you will never see this. You never know the thought process. People just tell you like, oh, it's learning from error, and our humans, we all learn from error. Yes, true, but how do we get there? And I would disagree with this approach. I would. I won't say this is a bad approach. I just don't think this is a neurally, psychologically accurate model of what happens in our brain and in our minds. Okay? All right? So think about it for yourselves. You know how we got here now. Okay? Not in the mathematical detail, but at least in the gist of the thought process while roughly working through the mathematics. And you can critique for yourself whether you are convinced of this approach or not. Okay? So what's the time we have? Okay, 11:20. Let's take a 5-minute break, and then the next thing we will talk about will be the implementation, and it will become a little bit clearer. Okay? So 5-minute break, and we will quickly try to finish up implementation, explanation, implementation. Okay? So yeah, 5-minute break, and then we'll come back to this. Okay, 5 minutes. So let's pick it up, and I think we should be able to finish this today, and then the next week we should be able to go into the Colab demo. Okay. So now this is, so previously was just a theory, so everything is mathematical and conceptual and symbols and all that. So now we're gonna like give a bit closer to, so how am I gonna implement it in a code, right? Because that's really what we wanna do, because as we do it in a code, we can see the guts of it, those concepts which we may or may not agree with. As we apply it in a code, it will get more concrete and you can have a better feel for whether you agree with it or not. So we try to implement it, and what this implementation is not, we're gonna not show the code today, we're not gonna do any coding today, but I'm gonna kind of walk through the pseudo code, kind of like the pseudo steps of how you might want to implement your model when you code it, okay? So the first step, again, we specify architecture, okay? And the architecture of a multi-layer perceptron, okay? Let's use an example that we want to do a multi-layer perceptron that is a 10 by 8 by 4, okay? In vector notation, we would say that this is a, we draw it like this, 10 by 1, this is AI, and then this is AIH. It's a bit smaller. And this is going to be a 10 by 8. This is going to be a 4. So 4 by 1, this is AJ, this is going to be 8 by 4. Okay, so we would do it this way, okay, conceptually, and so that when we implement it in the code, our code will have vectors, 3 vectors, and 2 arrays of these sizes. If it were that we were going to implement a 10 by 8 by 4. We could do a 20 by 4 by 10. It will look like this, right? Okay, so this one is a kind of a, trumpet kind of shrinking. This one is a narrow one and then opens up. You can do more, right? You can imagine, right? So this is how to visualize your architecture. This is how you would do it. So we specify the architecture, okay? So when you implement it, you will specify the architecture as such. Then, in this manner, okay? And you will also specify, obviously, the same steps to always do, the learning rule. Okay? Now, up to this point, we have said that the learning, the activity, AJ, could be linearly related to the product of W and AI, okay? Or, which is not useful, right? More useful is it could be actually equals to a function of the W dot AI, right? What function is it, though? We haven't talked about actually what function is it. We just know that it seemed like any function would work, okay, as far as the mathematical proofs go. So that's where Hinton suggests, well, a good function, he doesn't like the binarized ReLU, right, because it seems so hard, is it? No, don't want that one, okay? Seems such unrealistically categorical, right? Because life or biology is not so rigid. Seems to be more smooth, okay? So he specifies a learning rule such that, learning rule is about the updating, and that takes on from the activation function. So the activation function is the one that's like that. But let's say the learning rule he talks about, it's not the Hebbian one, but it's the Rescola-Wagner learning rule, the delta rule, okay? Sorry. But the learning rule is like this, okay? The change in the weights of j to I, not ij, okay? J to I at the next time instance, okay? This is critical. Is equals to eta of I'll talk about what eta is. The J. Alpha. And the previous change in weights at time t, where eta is 0. Okay, this is the learning rule, and we'll talk about the nonlinear function after this one. Okay, the learning rule, first things to note, it's very important, it is in the direction of j to I. So subsequent to prior. That's the weight you update. Okay, so the new weight for j to I, okay, between j to I, okay, is going to be equals to, this is the learning rate okay, and this scalar will modulate how much contribution the error, delta J, okay, has in the weight updating, right? Okay? And the other term here is what we call momentum. And this is a scalar also that will determine how the previous weight contributes to the new weight. Okay? So imagine this. I have some new information, some new error that's encoded in delta J. And I will use that to update my weight. But I also know my weight previously had some value, right? Do I want to completely erase that? No, maybe what I've learned has value too. So I will have some momentum to hold me back. So these two, eta and alpha, are in balance, such that if I want it to learn more from new stuff, then I will make eta bigger. If I want it to be more conservative, don't forget so easily, then I will make alpha bigger. And the two must add up to 1, okay? So that if I want it to be unbiased, if I want my network to learn equally from new, but also equally from the old, then I will make eta and alpha 0.5, 0.5, okay? But if I want it to completely forget what it learned before, then I will make alpha 0, and I'll make eta 1, okay? But if I want it to never learn, then I'll just make alpha 1 and eta 0. Okay? That's the manipulation here. That's what all these three mean. Make their range from 0 to 1, and their sum must be equal to 0. Okay? And because it is Ji, that is the backprop part. And because it is backprop of the delta J, it is the error backpropagation. That's what this learning rule is doing. Okay? So this is how the weights are updated. Not Hebbian. It doesn't care about the neighbors. It only cares about how it activated relative to some ideal that there is, which we don't know where it gets. Okay? And then that's where, now this is the specify activation function, okay, that nonlinear function which specify that nonlinear function that we haven't talked about up to this point. We assume that there's some function and generally it will achieve gradient descent. So what function though? What f? It doesn't like the binarized ReLU, but suggests this one. What's this? In here, I use I as like the prior layer, okay? So prior to the next layer, the previous layer to the subsequent layer. So this will be H1 to H2, or H2 to J, okay? All right, so note okay, so when we talk about this, I use I to J in just to exemplify the formula, but it applies for H1 to H2, H2 to J. What does this look like? Looks like this. It's a sigmoid shape. Okay? And because the proof of the math shows us that any general function will give us gradient descent, so we can use this one, no worries. And this is Aj of f. Remember, it actually wants the derivative. If you go back to your notes, the math actually wants the derivative to modify the delta. Okay, so not only is the activation function to decide the activity of the node, the activation function, the derivative of it, will be used to modulate the delta in order to achieve gradient descent. Okay, that's what the math was suggesting to us. So what's this? This is actually AI minus AI. Go and work it out. Okay, the sigmoid shape, the derivative of it is really the A minus 1 minus AI. It's very simple. It's very weird, right? Okay. Or if it is AI 1 minus AI is actually AJ. It's just a mathematical form. It can be outputted as well, right? It's just a form. Okay, so that's the architecture, the learning rule, and the activation function that we will implement. All right. Then the fourth is to well. Let me go to it. 4. We now apply architecture, learning rule, and the activation into the pipeline. Why is it pipeline? There's a procedure. The first step of the pipeline, feed forward. As we said, this is a fully connected feed forward layer. So the first thing to do is feed forward. Feed forward what? Feed forward the activity. So for I in 1 to size of W. This is pseudocode. Like if you have W being the size of the input to the by the output, right? So then you loop through the inputs to the output. You apply the activation function. Aj is equals to this is the same form as the sigmoid. I'm just writing it in one line. Okay? So first, feed forward activity. That's the first thing you do. You set up your architecture with your W arrays, then you say that, okay, I'm going to make AH2 equals to AH1 equals to A1 times W, right? But with the sigmoid function, so that the AH2 is equal to the sigmoid of the WAI. Okay, so do that, and then AH2, you know, for A, H, and J, right? You do that over the layers. Do it for AI to H, H to J, right? Or I to H1, H1 to H2, H to H3, H3 to J. So feed forward the activity starting from AI, propagating forward to AJ. That's the first step. Second step, compute. After you've now gotten an AJ, right? Because if you feed forward, the result is you're going to get the wave. The result is you get AJ. If you get an AJ, compute delta J, okay, at output. Okay, where delta J is equals to AT minus AJ. Remember, it's the derivative, right? It's the derivative because the activation function is f. The derivative of f is AJ1 minus AJ. Okay, you can go and work it out, right? If you want, I can do it next week. I do have it, but you can go and try it out. Okay, C proof. Try proof yourself. Okay? So that's step 2. Okay, we have feed forward the activity so that we get AJ. With AJ, therefore we can compute AT minus AJ, the delta modulated by the derivative, which will give us the generalized capacity to achieve gradient descent. The next. .3 backprop. Okay, backprop the delta J now to change the weights of the J to I direction. Okay, previously we were going I to J, I to H, H to J. Now we're going J to H, H to I, backwards. Okay, so we backprop the delta J to change weights of Ji. So that will be such that apply that function, the eta delta J AI, where AI is, because this is Ji, so the AI is AI. But if it is JH, then the AI is AH, okay? Right? It's the prior, okay? Okay, vector notation wise, I have, right? Yeah, okay. then okay, then this is how the cycle is going. Okay, so just to reiterate, this part is 1, this part is 2, and this part is 3. Okay, I'm just doing it as single layer first. Okay, I'm going to expand it to the hidden layer in a bit. Okay, so again, to be very, 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 very clear, draw it out as nodes. Let's say I have delta is a vector, don't forget. Okay, don't forget. So that this is going to be K by R dimensionality. This is going to be 1 by R, 1 by K, right? K by R. You can do this. Sorry, no. You can do this so that you get K by R. Transpose the other, flip the order, you get K by R. So that K by R gives you K by R plus K by R. Okay. Simple. If it is without hidden layer, this is what you would do for the feed forward. Calculate delta, backprop to change the weights. So Ij is when we feed forward, but that same weight becomes Ji when we backprop. Okay? All right? So in fact, it's equivalent, the concept of it. All right? Okay, the previous, this same position in the array, wherever the change was, now you change it but relative to the backward direction. Okay, so if this is clear like this at this stage, now this is the nightmare, the real nightmare scenario. Okay, because this is about output layer, so and then this is assume no hidden units. Okay? But that's not what we want. We have hidden units. So, wow, interesting. Okay, so then what should I do? 我会出来先, hang on. concentration. I didn't know that happens. Okay. Give me a second. Yeah. 你们也可以 like just scan it. Yep, okay. 可以吗? Well, I've got it. I will put it up, but you guys can get it? You won't get it. Okay, so what I'll do is I'll delete the earlier slides, then it'll give me enough space. Let me just go to the, yeah, and 这个可以删掉吗? Oh, yeah, 就直接在这里去。不是，这个，啊。All right, so let's carry on. Now this is the last part. So which we do, okay? Then delta hidden is equals to, remember, the activity of, same thing, the derivative form of the activation function, okay? But, and then we, this is just the delta J part, and then weighted by the weights. Yeah, because you go back to your notes, it is the delta J weighted by the weights and then similarly modulated by the derivative of the activation function. So the delta H, which is a 1 by K1 size, okay, is, and this is 1 by K1 size, 1 by K1, this is 1 by R, and this is R by K1 size. So that is all 1 by KR. And just to hash it out, so in other words, the hidden delta is going to be some modulation of the actual delta J. The delta H is some modulation of the delta J and the weights J to H. Okay? So these are the weights J to H, and this is delta J. They go into the delta H. And how are we going to do that? So I'm going to draw a network. I didn't want to draw this before because it's really crazy. Okay? I'm going to do, let's use red. And then let's use blue. Okay? Okay, so this is how it will look like, the full glory of the error backprop model, okay? The full nightmare, rather. I don't do K1. I'll just do that this is H1, okay? And then this is a H2, okay? And this 1 is not the same level as H. It is a subscript, so it's the first node of layer H, and this is the second node of layer H, okay? And this one will be, as we know, J1 to AJ3, okay? And it looks like this. You can imagine. Use the color so that you can differentiate where all the weights are going, okay? So the first step is to feed forward. Feed forward, no problem. We know that this is I1 and this is H1. This is I2, H1, I3, H1, I4, H1, okay? And this is going to be I1, H2, I2, H2, I3, H2, and I4, H2, okay? Similarly, this is going to be H1, J1, H1, J2, H1, J3, and this is going to be H2, J1, H2, J2, and H3, sorry, H2, J3, okay? So feed forward, stage 1, no problem. Just take this, multiply by this, apply the sigmoid function to get this. Then take this, multiply by this, apply the sigmoid function, you get this. Okay? Then you do step 2, calculate the delta. No problem also. Delta J1, delta J2, delta J3, right? Which is equals to AT minus AJ, AJ1 minus AJ, right? Okay? So accordingly, all right? So AJ1, 1, 1, right? This is the index, V1. Then you apply that to J2, J3, okay? Then I'm going to use green to circle. Use the delta J, because this is the output delta J to modulate. Let's focus on the red node, the red hidden node. Okay, this is delta J is used to compute the change in the hidden weight, this one. So that the new green weight of J to H now, J1 to H1, the reverse direction, okay? And also, sorry, I was wrong. Let's see how we can do this nicely. Not this one, draw the wrong line, sorry. Excuse me. Okay, should be this one. Okay, that's why it gets nightmare. H2 T plus 1. Okay, so that it becomes J1 H2 is updated. You see why? Because it is this delta calculated for this node, AJ1, and AJ1 is connected to the hidden layer by WJ1H1 and WJ1H2, right? Okay, so in other words, this delta can only change the weights for these two green reverse weights, right? This delta cannot affect the other weights. Make sense? Feed forward is those weight relationship, but feed back, you have to flip things around and realize that it's now sort of the delta is now the input, if you want to put it that way. Okay? So similarly, use yellow. This one can only affect this one and this one in terms of the change in weights. JH direction. Okay? All right? Okay. So, and not only that, further nightmare, not only does it only use to calculate the change in weights, it's also used to calculate delta H here. Okay? Right? You use the hidden nodes activity minus for the activation function derivative, but you multiply that with the delta J coming in but modulated by this. So these two terms, this one is this one, and this one is this one, okay? And this one is this one, right? And this one is this one. Can you see where all the pieces are fit? Okay? So in order to calculate a delta H, you are taking pieces from so many places. Okay, so that will be how the hidden layer delta is computed. And once the hidden layer delta is computed, it will backprop further. Okay? So assuming you have H minus 1, then this will go into H minus 1. And H minus 2, if you have deeper layers in there, then you will subsequently repeat this cycle over and over and over again. Okay? So that, we'll finish with this note. Okay? Delta H oh no, I already did that. Yeah, sorry. So yeah, the dimensionality, I already got that here. So this is done. Don't need that. Okay, the dimensionality, yeah, so that you will get a delta H, which is a vector calculated from the equation, which will give you that correct dimensionality. Okay. Okay, so this is the implementation. Okay, you have. So quickly revise, and then we'll finish up. First, you feed forward regularly using the sigmoid function. Okay. Then, once you hit the output, you can then compute the delta J with respect to the target output. If you forgot what AT is, go back to the problem set. Okay. So that we can get the AT minus the AJ that we get, modulated by the derivative function, and then you get delta J. Once you get delta J, you can then use it to compute the change in weights, okay? And use that change in weights to update the original weights according to the learning rate and the momentum that you want. And with that, that's if you are at the output layer. But if you have hidden layers, you can do more. You can then use this delta output to also further not just calculate the change in weights, but also calculate the hidden layers, that delta, okay? Which will be itself a modulation of its own activity, the subsequent delta, okay, quantity, and also the previous weight. So to clarify, this is about, this is at the previous, before you update it, right? Because you realize you update this weight, this is t plus 1. You calculated this thing at t plus 1. But you don't want to use the t plus 1 to calculate, this does not affect, right? It is this previous weight that affects it. Make sense? because it was the previous weight that caused the error. Okay, so you want to use that previous weight to modulate the, to reflect the hidden error. Okay, so if you use the new updated weight, then it's all messed up, doesn't make sense. Okay, so I tell you this now, but when you code it, you're gonna get lost. Okay, you're gonna say like, wait, which version of which weight am I using, in which direction I'm going, and which error I'm using. Okay, yeah, I know the struggle. So just to let you know that you will struggle with it, and that's normal and that's okay. All right, but that's how this looks like. That's how backprop works, as you have in the chapter. Okay, my personal feeling is it's a mess. I do not like it. I think it works as an engineering solution. It's a very engineering thing. To me, it's not really as elegant as I would like it to be. Not criticizing its power and its usefulness, but for me, my interest would be in a different direction. I would require more neural plausibility and psychological meaning to this. Here, it's just numbers being fit in a logical way. That's it. Yeah. Okay. But we do not throw the baby out with the bathwater. Perhaps there is some truth to this in the way our brain works, and it remains for people to go and study it and see. Okay. Always the perennial question is, okay, fine and good. The biggest question I think psychologists always ask, but where is the error? How did you calculate it? You can say AT minus AJ all works, Sure, but where? Where did it come from? Where is AT minus AJ? And that has not been answered to this day. So in LLM, AT minus AJ is some human being, rated the words or produced a word, and then the machine produced a word, and then some mathematicians say, okay, so this word is different because of this number. Okay? But when it comes to a human being, where is the AT? So my argument is because of that, it doesn't stand as a neurally plausible model. Okay? Unless you demonstrate to me otherwise. But I do not think that AT exists in the way this is framed. Yeah. And my clue to what I think actually is more correct is actually back to the Hopfield. I think that AT is the prior state of the self. So in other words, actually, I think autoencoding is more correct than error propagation to explain humans. Okay? There is an error. There is a discrepancy. So the autoencoding has an error in there. Okay? But it is not this AT thing. Okay? Moreover, I also do not think that there is backpropagation. I think the brain only has forward propagation. So how do you make some self-autoencoding error and forward propagate it and then show that it also works, it also learns in some way? Okay, so that will be a challenge. This is what I'm recently toying with. Haven't implemented or tried it yet, but this is the idea that I think makes more sense to me given these concepts that we have touched on so far in this class. We have touched on autoencoding, we have touched on this notion of error learning and propagation, right? I suggest to you that, and they did great work in the past, I suggest to you that now, if you care about biological and psychological plausibility, one suggestion is, hey, maybe it's not these, but it is a combination where you have autoencoding, you have the error of the autoencoding, and you have propagation, but it's only restricted to feed forward. Does that work? So I don't know. How does that work? Okay? Yeah. All right, so I'll end this today, very theoretical and conceptual session today. And then next week, we will talk about the coding, and then you will be able to do backpropagation. You'll be able to create your own LLM. Yeah, okay? Okay, any questions? No? Okay, If not, then that's it for today. You are still, assignment-wise, you are supposed to be working on the hot field network. It's due in May, so you have some time, okay? But although we are not talking about hot field network in class, feel free that if you have questions about the assignment, just feel free to raise it up or post it in the discussion as well, okay? All right, so that's it for today. Thank you so much. We'll see you next week.